Hi, everyone. Thank you for coming to my presentation. A word about me. My name is Joey. I've been in the cybersecurity industry for more than a decade. I participate in CTFs together with Pasten, and today I work as an independent consultant at my consulting firm, HYPR. So the story I'm going to tell you today is from a time before the internet, way back when. I'm talking, of course, about 2014. Now, obviously, there was plenty of internet in 2014, but 2014 was really the tail end of a phenomenon known as the offline LAN party, where you would gather together, everyone would bring their computers, you would take a switch, everyone would connect Ethernet cables to the switch, and you would play with each other all of the classic games, Unreal Tournament, Counter-Strike, whatever. But while you were doing this, you'd be connected to the local switch, and you wouldn't have access to the internet. Nowadays, you would just go to someone's home, connect to their Wi-Fi router, and be able to play with each other without worrying about any of this. But back then, home Wi-Fi routers weren't powerful enough to support this many people. And so in 2014, a friend of mine invited me and a couple dozen of his closest friends over to play some games. And there was a game that I had been playing for a few months before that called Spy Party. Have any of you heard of the game Spy Party? No. So Spy Party is a really cool game. It's a game for two people, where one player plays as a spy, walking around in this ballroom with a bunch of other bots, and has to complete a number of missions. And the other player is playing as a sniper, looking in through the window at all of the bots, and has to determine which one of them is the human being. So it's sort of like a reverse Turing test, where the player playing as the spy has to pretend to be a bot, while simultaneously completing a number of missions. So it's a really cool game, and I wanted to play it at this party. But unfortunately, Spy Party requires an internet connection. And I even had a number of licenses to the game because I'd played it with other friends elsewhere, but we weren't able to play it because we weren't connected to the internet at the time. And so, of course, I did what any of you would have done as well. I decided I'm going to build a private server for Spy Party so that I can play the game while I'm not connected to the internet. So we want to play the game. We're not connected to the internet. How do we start building a private server? So the very first thing we do is we open up Wireshark and we see what the communication of the game to the servers looks like. And we see a few interesting things. First of all, the authentication happens with Kerberos. So I double-click the game's exe file. I get a login screen. In the login screen, I enter my username and password. And I see that there's communication to the domain kerberos.spyparty.com in the Kerberos protocol. I'll talk about that a bit more afterwards. After that, there's communication with the game's lobby through the DNS lobby.spyparty.com. And finally, once I actually start the game, through the lobby I talk to other players, I choose someone I want to play with, I click connect to game. The game itself happens peer-to-peer between the two players playing the game. And why is this really, really good for me and for my attempts to build a private server? Because it means that I don't actually have to implement any of the game logic itself. Any of the bots walking around doing various things already happens within the client. All I have to do in order to build this private server is implement the authentication, implement the lobby and the matchmaking, and then the game itself will just run. So we get started. So what is Kerberos? Kerberos is an authentication protocol, most commonly used by Microsoft. It's not the prettiest protocol, and it's way overkill for an indie game like Spy Party. And so I start trying to figure out how I'm going to handle Kerberos. And so I reverse engineer the game and look for various symbols to do with Kerberos, try to understand the flow, and try to patch Kerberos out of the binary. Ideally, the flow from my perspective would be that Kerberos is compiled as a standalone DLL. I can look at all the functions from the DLL that are used by the game client. And each one of those I can either patch out or return some kind of hard-coded value. At the end of the day, I really only want two clients connected to one server, so I think I can hard-code a username, user1, and hard-code a second user, user2, and have two different clients. That's good enough for my purposes. Unfortunately, patching it out is much harder than I expected. First of all, because the developer compiled Kerberos statically into the binary, so there's no clear division between the game's code and Kerberos. But more than that, something weird is happening here. It looks like there are internal fields in the Kerberos struct that the developer is using for his own purposes, and he's calling internal Kerberos functions directly instead of calling functions that I would expect to be called. And so it's very, very hard to understand exactly where the line is and to make a clean split between the game's code and Kerberos' code. So after a while, I give up on that, and I say, OK, let's just spin up my own Kerberos server. Kerberos, there are two ways to spin it up. You can spin it up on a Windows server, or there's an open source implementation. You can spin up on a Linux server. I spin up a Linux server. I call it kerberos.spyparty.com. I redirect my own computer's, in my own computer's host file, I redirect kerberos.spyparty.com to the new Kerberos server that I've spun up. And it works. I've successfully authenticated with Kerberos. I get a ticket, and the game now tries to talk to lobby.spyparty.com. And so I start looking at the communication happening towards lobby.spyparty.com. And I see that the packets themselves that are being sent, they're not in some kind of known format. They look maybe encrypted, maybe compressed. Something's happening here, but they're not JSON, or they're not something human readable. There's no easily readable strings within them. And Kerberos only handles authentication, not encryption. So whatever's happening here in the code is something happening within the game client itself. And so I start reverse engineering. I open up IDA. I try to understand the various flows that are happening and understand what's handling packets. And eventually I find two classes. The code is in C++, so I find two classes called encoder and decoder that are responsible for handling the raw messages and turning them into various data packets that we can work with. And one of the really nice things I see in the code is that there's various assertion strings. So the developer wrote in his code, assert bits is less than or equal to 32. And within the compiled code, I can see that the file name here is arithmeticcoder.cpp. The line number is 437. And this is very helpful to understand both exactly what the flow is, and to understand here I have a variable v8. I don't know what v8 is, but after I see this assertion, I can assume that v8 is bits, whatever that means. And so I see that there's this objects for encoding and decoding, and they're using something called arithmeticcoding.cpp. Now, I have no idea what arithmetic coding is, but luckily I can search for it on Wikipedia, and Wikipedia explains how arithmetic coding works. Arithmetic coding is a compression algorithm that is theoretically optimal, and the way it works is you have a probability of each different symbol appearing. So a message is just a sequence of symbols one after another, and let's say that the probability of the symbol A appearing is 60%, the probability of the symbol B appearing is 20%, the probability of the symbol C appearing is 10%, and the probability of end of message being reached is also 10%. So how does arithmetic coding work? It encodes any sequence of symbols as a number between 0 and 1. So if the message starts with A, the message will be encoded as a number between 0 and 0.6. I then expand the range and again divide it by the probabilities. And if the next symbol is C, then the message is encoded as a number between 0.48 and 0.54. If the message then ends, I again expand the range. Any number between 0.534 and 0.54 will be encoded as the message AC. And so any message I want to send, I can send as a single number between 0 and 1. And obviously the catch is that as I get to more and more exact decimal numbers, I need more and more bits in order to be able to send that sequence of numbers. But if I know the probability table, then I'll be able to send any sequence of numbers. So now that we understand that we're looking for something to do with arithmetic coding, I start looking through the decompiled code and attempt to find something that looks like a probability table so I can implement arithmetic coding. And I search, and honestly the code is not that long. It's a few hundred opcodes at most, and there's nothing accessing any kind of external memory table. It doesn't seem like there's any kind of table here, and I'm not quite sure what to do. And eventually I just say, fuck it, there's no table, I don't know what's happening here. Maybe it's not arithmetic coding, but I'm just gonna blindly implement it in Python. And so I write Python code that looks like assembly, RAX equals RBX plus 2, terrible code. But after I write the code, I start deconstructing the objects, and it works. I have objects underneath the arithmetic coding that I understand. And then I go back to this, having implemented it. It looks like arithmetic coding. There's logic that's happening very similarly to arithmetic coding, but there's no table. What's happening here? And then I understand that the reason that there's no table is because the developer of the game just assumed that the probability of every symbol coming out is equal. Now, what happens if you have a compression algorithm and assume that the probability of every symbol coming out is equal? By definition, you can't compress the data because there's an equal chance of anything being happening. Not only that, the compression algorithm actually ends up expanding the amount of data that's being sent over the network. So we get through with the compression algorithm and we start decoding the packets themselves. And there are a few things that help out with this. The first is that there's some kind of scrambled log that's being written. So whenever a crash report is filed or a bug report is filed against the game, the game automatically attaches the scrambled log, and rather than trying to understand how it's scrambled or encrypted or whatever, I add a breakpoint to the code right when the logs are being printed to the, right when things are being printed to the log, and I print them out directly, so I can see what's happening as packets arrive. I can see a log like getting invitation, joining lobby, and things like that that help me understand what each packet does. And also every time data passes through the encoder or the decoder, when I run the real client against the real server, I can print out the values that are returned and slowly start to understand the different data structures that are being sent. And as I understand the different data structures being sent, here's the WinDebug script that I use to understand. The exact things that are happening aren't important, but I set breakpoints at various addresses and decode values. I start writing a Wireshark plugin as well to parse the different packet types. And at the end I have a Wireshark plugin that allows me to parse the spy party protocol, and I can see what packets I've handled, what packets I don't handle. I can see the inner information within the packets and start filling them out, run the game against the real server, see what the flow looks like, run the game against my server, see what the flow looks like, and understand over time exactly what packets I'm missing. And slowly I started to implement the different packet types. I implement the chat packet, and I can connect two clients to my server and chat between them. I implement joining rooms. I implement invitations. So one client sends an invitation to the game to the other client. The second client sees a pop-up saying, this player wants to play with you. I can click accept on the invitation, and then something is sent that's called a candidate packet. Here's some example code from the server of getting data from one of the packets, encoding a response to either that client or the appropriate client. So a candidate packet. Before we talk about candidate packets, how do two computers connect to each other on the internet? So we have two clients who want to connect to each other and want to play a game that's peer-to-peer. The simplest thing to do would be for both computers to just connect to the IP address of the other computer. But in the real world, this is unlikely to work because chances are that the computers are behind NATs. And if they're behind the NAT, then the IP address of the computer is actually the IP address of their router. What might happen is that one computer is behind a NAT and the other computer is not behind a NAT, and then one computer won't be able to talk to the second, but the second will be able to start talking to the first, and then they'll be able to establish a connection. Another thing that might happen, they might both be behind NATs, but they might both be behind the same NAT. So it might be that me and someone else are playing a game at the same house, and so rather than going over the internet to communicate with each other, we can communicate over our local IP address directly between each other. If we're both behind different NATs, then we need some kind of advanced technique. We could use, for example, UDP hole punching in order to establish a connection between them. And if none of those other things work, we could always use a relay, have a server on the internet that both computers can connect to that's just responsible for passing packets between each other. So those are all various ways that computers can connect. And there's a protocol called ICE, Internet Connectivity Establishment, that handles this exact problem, that allows two computers to connect to each other. And it works by sending a sequence of candidate packets, where each packet is one of those ways I described of how two computers can connect to each other. And it looks something like this in the logs that are sent by Spy Party. But when I look at the data that's actually in the candidate packet that this client sends to the server, there's just a binary blob at the end of it that looks like it's somehow encrypted, encoded. It doesn't look readable. It doesn't look something that I can decode. And more than that, when I open up two legitimate clients against the legitimate server, the first client sends some kind of binary blob to the server. The second client receives some kind of binary blob from the server, but the binary blobs are different from each other. The server's doing something and changing them in between. And I try reverse engineering the code, but at this point there's a huge amount of code. Unlike the decoder before that was just a couple hundred opcode, there's hundreds of functions that each call each other and do weird logic, and it's really hard for me to understand and follow along and determine what exactly this data is, why it's being changed, what's happening here. And here I get stuck for quite a while, a number of months in fact, where every once in a while I'll spend a weekend, spend a few hours coming back to it, trying to understand what's happening, and I'm just stuck. Until eventually I find encryption. Now, usually when experienced reverse engineers say that they find encryption, they mean something like, I found a constant that's part of AES's S-box, or I found a constant that reminds me of MD5, or something like that. When I found encryption, I literally mean, I found the string in the code, AES 256 CTS mode with 96-bit SHA-1 HMAC. So I take this string and I search for it on Google, and it turns out that this string is actually part of the Kerberos library. And what's happening here is that the developer is using internal Kerberos things, and I've actually been spending the last few months reverse engineering code from Kerberos that's actually open source. And so now that I understand what this is, I can get a much better grasp of what's happening. And it turns out that there's an internal mechanism in Kerberos called priv. And after the client connects to the server via Kerberos, the server can use the functions readpriv and makepriv to encrypt and decrypt messages to the client. So what's happening is that the client takes that string we saw before, it encrypts it with makepriv candidate, the server decrypts it, encrypts it with the second client's key, and sends it to the client. Now, this isn't something that you're supposed to use as a user of Kerberos. It's a pretty internal mechanism. But now that we understand that this is what's happening, we can easily implement it ourselves. There's a wrapper for Kerberos in Python. The server I was implementing was in Python called PyKRBV. That can call these functions for me directly. And I try calling the functions, and I get an error, invalid net address. Now, it's a pretty weird error to get because I'm encrypting and decrypting data. There's nothing that I'm doing here that has anything to do with network addresses. But I have the source code available to me, so I look in and understand where invalid net address is being passed from. And it turns out that when Kerberos encrypts data, it adds a bunch of metadata to the beginning of the packet. And that metadata includes information about the connection that's being sent on. So I have the IP address of the connection as part of the packet, and when you decrypt, the data is being checked as well to see that it matches what's being sent. So the logic of Kerberos itself is happening in an SO that's wrapped by my Python code as part of PyKRBV. And so I attach GDB to my Python. I set a breakpoint within the Kerberos shared object in order to skip over that check. I skip over the check, and it works. The candidate packet is decrypted, and I get a string that works and looks exactly like what I want it to be. But then I dive in a bit further to understand what exactly happened here. Why does the check fail? And so I take a look at the comparison that's being had. On one side, I have the IP addresses of my actual connection. So I have the server is on IP 10.0.01 port 52668. And instead of comparing to that, the data that's in the packet is the IP address 1.2.3.4 on port 0x0102. And on the other side, it's being compared instead of to the real value to 5.6.7.8 on port 0x0506. What's happening here? What's happening here is that the developer is using an internal Kerberos API, had to pass a number of parameters, didn't understand what the proper parameters to pass were, and so instead of figuring it out properly, since he controls both the client and the server, he just pushed in a bunch of garbage hard-coded values and the entire code started working for him. And so that's the way it's been deployed up until today. Once we have the candidate packing, we can more or less play with each other. We need to parse the rest of the types. There are a few packets that are still sent during the game, like when a game finishes, when someone wins, etc. And we can play the game. And that would more or less be the end of the story. Except that a couple of years later, I decided on a lark to send an email to the developer of the game. Dear Chris, I was playing Spy Party. I built a private server for your game. And his response was, well, less than pleasant. Nah, I'm just kidding. He loved it. He was so excited. This was the first time anyone had dove into his game like this. We talked a lot about the different issues that we had discovered. I showed him the Wireshark plugin. I'm sure while he was developing the game, he had nowhere near this kind of tooling in order to be able to understand various things that were happening on the network. One of the things that might have been missing from the story is actually playing the game. I spent a number of months building the server, but once I finished building the server, I wasn't really interested in the game anymore. I just built the server for the challenge of it, and because at this point it was exciting. A funny story about that is that when you're in the lobby, it's an indie game. It was relatively small back then. I think it's somewhat bigger now, but I don't know. I haven't played it in a number of years. And so when you get into the lobby, often there'll be no other players there. And you'll set up a notification so that when someone joins the lobby, you'll get an alert on your computer, and then you can ask them if you want to play. And there's statistics for the various players. And so for one of the accounts that I created solely for the purpose of building the project, I had a statistic somewhere along the line of 200 hours played, 0 games played. And whenever someone would enter the lobby and see that I was there, they would be excited. Oh, there's someone who I can play with. And they would say, hey, Joey, want to play the game? And I would say to them, sorry, I can't. I'm working on a project. And I would just be in the lobby idling while I was looking at the network traffic to try to understand exactly what's happening. The last story that I promised, but unfortunately I'm going to have to cut, and you can catch me in the hallway afterwards if you have any questions about it, is that while building the game, while working on developing the game, something was wrong with the internet. There was some kind of problem where occasionally weird packets would be sent, things wouldn't work properly. And so I decided to dive into that and understand what exactly is happening and try to fix the internet. And it turned out that something was deeply broken with the internet in my entire country, and I managed to fix it at the end of the story. So catch me in the hallway if you want to hear that part of the story. Any questions?
Thank you so much for that. That was really exciting. And yeah, it's a good thing that lunch is coming up because that's worth sacrificing for hearing the other side of the story. Thank you so much, Joey. Who's got questions? We can take like 2 or 3 before we wrap up. Could you please stand up so Joey can see you as well? Thank you.
I have a question. Did you ever find out why they used Kerberos to build their game? It's like using a Ferrari to cut your lawn.
So I think the developer was just familiar with Kerberos from the past. I actually looked into, when I was searching for Kerberos and the connection of the game, the developer has a number of posts in the Kerberos forums and actually made a number of changes to the Kerberos protocol on his end, fixed a number of bugs, and rather than committing them upstream, he just fixed them locally and kept working himself on his fork of the code. And so the code that he was running was not exactly the code that was in the official open source library.
I understand. Thank you.
Cool, thank you. Any other questions? One over here.
Sorry, so I didn't quite understand how you had access to the game code. You said in your presentation that you looked at how Kerberos was called in the code, and you said that it wasn't easy to split the two apart. But how could you look at the game code itself? Was it open source?
The game wasn't open source. Everything I did was based on reverse engineering the code. So I was looking at the code in IDA, I was looking at the assembly code, I was decompiling it within IDA in order to understand what was happening, and that was why it was so difficult to understand the flows of the code that were happening. So for example, when the code called code from Kerberos, I didn't understand right away that the code that I was trying to decompile was actually code from Kerberos and not part of the logic that the developer wrote.